So I want to start by going back and looking at Ampere's law. Okay, I want to go back and discuss Ampere's law again because there's a problem with Ampere's law. And we see the problem when we consider a charging capacitor. So imagine you have a wire carrying current, I, and you have a capacitor. This plate has charge plus Q. This plate has charge minus Q. Current is going this way. And I'll call this current I sub C, calling it the conduction current. You'll see why I'm calling it the conduction current. This is due to the flow of electrons in the conductor. And so the electrons are going basically like this, like that. As the capacitor charges up. And let's assume the wire is long. So let's assume we have a very long wire that we can calculate the magnetic field due to a long wire. And I'm going to calculate the magnetic field at a point A here from the wire. I can just use Ampere's law. Okay? In the current form, we know that Ampere's law says that the integral of B dot ds is equal to mu naught times I enclosed. And that's the current that's enclosed in the loop over which I'm integrating the magnetic field. So let me draw a loop. Actually, let me use a different color. There's my loop, okay, and I didn't draw it very symmetrically, but this is the radius of the loop. We'll call it R sub A. And I apply this principle. I say, okay, well, the magnetic field is going to be along the direction of the loop, and I'm going to integrate the magnetic field in the same direction as ds. So let me say that. I'm going to integrate in the B in this direction, magnetic field points, this way. So I'll get, okay, B times 2 pi r, because I know the magnetic field is going to be the same at any value of r because of symmetry, is mu naught times I enclosed. What's enclosed in here is the conduction current, basically the current in the wire. And I say B is mu naught I sub C over 2 pi r. And you're familiar with that. That's not a big deal. Okay? But what if, instead of calculating the field at this point, I want to calculate the field at this point? Oops. What if I want to calculate the field at this point and I want to apply Ampere's law? Then what? Okay. And I apologize for the fact that the video is not good. I'm just going to continue lecturing and you can watch the video that I'll upload after class. So what if I try to do the calculation at this point? Well, there's no current enclosed here. Okay. So there's no current enclosed. So does that mean B is 0? And it can't be. If you actually measure the field here, it's going to be almost the same as the field here. That's because there's edge effects, etc. here. I mean, maybe you can try to calculate the field here using Biot-Savart law, but it's going to be kind of complicated. Okay, it would be very difficult to do. But Ampere's law says that the field here is 0. I know it ain't 0, so there's something wrong here. Okay, there's something wrong with Ampere's law written as is. And let me show you another issue that comes up with it. Remember that Ampere's law is valid for any surface enclosed by the loop. Okay? Ampere's law is valid for any surface that's enclosed by the loop. So let's think about this. If I have a current I, and I'm not going to do the capacitor for now. Let's say I have a current I, like so, and I draw a surface. I'll call that surface 1, and I know the current through this surface is going to be I. In fact, I can say that the integral, so let's look at this surface S1, the integral of the current density dotted and I'll use capital S. The integral of the current density dotted with ds, capital S, is plus or minus I. That just tells me that the plus or minus is there because of the fact that there's an ambiguity in my normal to the surface when I have an open surface. Let's say I choose another surface that's enclosed by this loop, like this one. My integral of J over the other surface is also going to be equal to plus or minus I, because I have the same current going through either surface. Now notice that these two surfaces together form a closed surface. If I take those two surfaces and put them together, they form a closed surface. So I have some current going in and some current going out. So over the closed surface, I get 0. Because remember, if I define the unit vector n points outward away from the surface when you have an enclosed surface. So one of these is going to give me, one of these integrals is going to be plus I, and the other integral is going to give me minus I. And so the sum will give me 0. So Ampere's law says then if I have a closed surface and I integrate the current density of a closed surface, I have to get 0. And what if there's a source of charge inside the surface, though? I'm sorry. What if there's a source of current inside the surface? If there's a source of current inside the surface, then there's going to be a net flow of charge coming out of the surface. Okay? There's going to be a flux of charge coming out of the surface per unit time. So somehow this is not consistent with Ampere's law. Okay, if I have a source in here, I have to be able to account for it. This integral cannot be zero if I have a source in here. But Ampere's law says that since this is true for any surface, if I have a closed surface, this integral has to be zero in any case. So something's wrong with Ampere's law in that form. And Maxwell recognized this. Okay, Maxwell recognized this, and so his job was to come up with a solution for it. Now, again, let's look at the charging capacitor. Let's use those two surfaces. Again, if I use those two surfaces, Ampere's law, using the surface enclosed by this loop, gives me the correct expression for the magnetic field. But if I use this surface that's enclosed by the loop, Ampere's law does not give me the right expression because there is no current penetrating this outer surface. And that's because inside the closed surface I have a source of charge. So through surface 1, which is this one, I get the integral of B dot ds as mu naught I enclosed, but through surface 2, since there's no current penetrating the surface, this outer surface, you can imagine if I took a hat, and I just put a hat over here, okay, and this the surface of that, we're talking about, let's say, the surface of the hat, no current goes through that surface. Oh, what is the difference between source of charge and source of current? Basically, I'm talking about a time-dependent charge. That's why I say source of current. Okay. That's the only difference. I'm saying that there's some charge flowing out of the surface. Just like water flowing out of a surface. And maybe I misspoke when I said source of charge, but I really should have said source of current. Just like you would have water flowing out of a surface. So you just make the connection with the water flowing out of the surface. There's something flowing out of here. If something's flowing out of here, there's got to be a source in here. Okay, like if you have a water faucet inside here. Okay. So there's got to be some source that's pushing the electrons out of the surface. Well, just think about it in terms of a water faucet. Just imagine this is a pipe of water, or water flowing in a pipe. Okay? And this is a closed surface. Whatever goes into the surface comes out of the surface. Okay? And if whatever goes into the surface equals to whatever goes out of the surface, then that integral is going to be zero. But now if I have a water faucet inside the surface, then I have to have a net flow out of the surface. So think of the current, the source of current as maybe like a water faucet, or actually like a drain. So let's go back to this. Inside this closed surface, I do have a source. So what did Maxwell do? He said, maybe what we need to do is introduce another term here that's equal to epsilon naught d phi sub e dt. Which is the same as this term here is the same as this. And this is an open surface. And he was using the idea, I mean, this is what he was looking at. He was saying, well, Faraday's law looks like this. A changing magnetic field induces an electric field. So he said that if nature is symmetric, then a changing electric field will produce a magnetic field. And that's what this is a statement of. This tells you that a changing electric field produces a magnetic field. And now if you remember from Gauss's law,
this meeting is being recorded.
If you remember from Gauss's law that this integral is related to charge. And so then it makes sense that the derivative of this integral is related to current. This term is called a displacement current. And so we call it I sub d equals epsilon naught d phi sub e over dt. We call it the displacement current. And this correction eliminates the contradiction that we have with the original version of Ampere's law. So that now Ampere's law looks like this. Oops. So Ampere's law looks like this now. Okay? And this term is called a displacement current. You can also write it in the following way. Remember, this is the integral of the current density, so you can always write it like this. Where the integral of j sub c dot nda is just the current. Okay. And then this would be, again, the current density, the displacement current density. Okay, so then, I mean, this was a big deal. Oops. This is a big deal. This made Ampere's law consistent. Okay. And it was a big deal now because now you have really four important equations. There's really four important equations in physics, in E&M, that can describe almost everything that we know in this subject area. And you can take those equations and manipulate them and come up with interesting things. So I'm going to talk about that in a little bit. Okay. So the new form of Ampere's law then implies that both currents and time-varying electric fields produce magnetic fields. That term that comes up. So it's called a displacement current. It's not a great name, but that's the name that they gave it. Okay. That's why I wrote I sub C, because I sub C is actually the real conduction current, and I sub D is what happens in here, the displacement current. Okay, so we need to take a look to see if this is consistent. So I'm going to go back and look at what all this means. So let's take a look at surface, and for some reason in my notes I changed orientation of everything. So let me draw a picture that's consistent with my notes. Let me draw a capacitor again. And let's let the current go this way this time. Doesn't matter. So let's make this minus Q, this plus Q. The electric field in between the plates is this way. By the way, I did send you folks a video on this topic. I think it was last week. You should watch it. It's a video by Walter Lewin that goes through this calculation in a lot more detail than I will go through. Okay. And he does a great job in describing this and all the details of it. So I'm not going to go through all the details, but I'm going to go through the main idea. Okay, so I want to apply Ampere's law to two surfaces. Let's draw I here. And this is the conduction current. This is surface 2, this is surface 1. I want to apply Ampere's law. Okay. I guess I have these reversed. Let's apply Ampere's law using surface 1. Okay. So in this surface, what do I have? What's punching through the surface? Right? The current's punching through the surface right here. Okay? I'm just considering the blue surface. Okay, I'm punching through that surface. So then I say, okay, well, the integral of B dot ds is mu naught I enclosed. And again, we know that the field is going to be symmetric around this loop. Remember, we're looking at this loop, and we're looking about this surface that encloses the loop. So this can give me just B times 2 pi r mu naught. What's penetrating the conduction current? Which is what we had before. Now, let's look at S2, which is the flat surface that's enclosed by the loop. When I look at the flat surface that's enclosed by the loop, this guy does not penetrate this surface because we're in between the plates of the capacitor. That means I have to use this term. So I have to write down that the integral of B dot ds is equal to mu naught epsilon naught d phi sub e over dt. So now I got to figure out what this flux is. And really I'm talking about the electric flux through S2. Okay, so this term is the electric flux through S2. And basically the electric flux is just contained within the area of the capacitor. The field out here is 0. So I want to calculate the integral of E dot n dA in here. Well, E is constant between the plates. All right, E is uniform in between the plates. So that means, and then E dot n is 1, I mean the dot product, these two are going to be parallel to each other. I'm going to choose my normal that way, consistent with the fact, with the integration direction by the right-hand rule. And so this integral is just going to be E times A. But E is changing because the capacitor is charging up. So let's look at this term. I can pull the A out of here. Now E is, if for a parallel plate, E is, if you remember from earlier in the class, sigma over epsilon naught. So let me put sigma over epsilon naught here. The epsilon naughts cancel. And then I'm left with, so this term right now, and I'm going to write over here because I'm running out of space. So far I have the following. These guys cancel, and I have now what's sigma? Sigma is the charge per unit area. So that means these guys cancel. What's dq dt? Well, the dq dt is the same as the dq dt over here, so this is mu naught I conduction. And you can see if I just do B times 2 pi r, I'm going to get the same expression as I did using the first surface. So I get the same field when I apply it to this surface or that surface. I get the same exact equation for the field, whichever surface I use. So really, the displacement current here is really going to be equal to the conduction current in here. Which I have this worked out in your notes. So the displacement current is equal to the current through S1. This guarantees what's called continuity, meaning that whatever goes into a surface has to come out of the surface. Remember the discussion I said before that if I have a current going through a closed surface, the integral of J dot n dA or ds over the closed surface is 0 unless I have a source there. If I have a source inside here, like again, go back to the water faucet analogy. If I have a source of current in here, then there's going to be a net flow of charge per unit time coming out of here. And so I have to account for that. So that's going to be equal to minus dq over dt. With the minus sign means the charge is flowing out. Okay, this guarantees continuity. That means that whatever's going in comes out. That's what I mean by continuity. Some books discuss the idea of continuity, some books don't. So suppose I have a capacitor is fully charged. What is the displacement current? Well, if the capacitor is fully charged, this is 0, then the electric field is not changing. Right? If the capacitor is fully charged, electric field between the plates ain't changing. Q is constant. And so this term is going to be 0, so my displacement current is 0. And like I said before, the displacement current here is going to be the same as the conduction current. And if I have a capacitor that's charging, for example, in the second example here, if I have a capacitor that's charging with a current of 0.1 amp, and we're given a capacitor that has square plates, and what is the displacement current? Again, the displacement current will be the same as the conduction current. But what is the time rate of change in the electric flux? What is the time? What is this term in that particular problem? Well, if I sub d is 0.1 amp and it's equal to epsilon naught d phi sub e over dt, then isn't it true then that d phi sub e over dt is the 0.1 amps over epsilon naught? So it's going to be 0.1 amps over 8.85 times 10 to the minus 12th. And you get 11 times 10 to the 9th. volt meter per second. Or this unit is also the Newton per Coulomb meter squared second. That's the other unit. Okay. The last question says use Ampere's law to calculate the magnetic field between the plates, but we've already done that in the previous example, so I'm not going to go through that. Okay, the previous example, I do go through that example, so I'm not going to do that here.